So question 2, why does heme C typically have a higher redox potential than heme B? All right, this has a lot to do with the ligands to our iron. So if you remember a couple things, iron has two choices for the most part in biochemistry. It can cycle easily between iron 2 and iron 3. Right? Occasionally we see iron 4, but that's we're not going to cover that in great detail in this class. Now, with the iron in the porphyrin ring and the hemes, right, that's indicated by these little ovals above and below the iron here, right? But iron also has axial ligands that bind on the top and bottom of the ring, right? And in the case of heme B, right, these are both nitrogens from histidine. All right, well, if we think about the side chain of histidine, right, just to review, metals like to bind to lone pairs of electrons. Right? That's what's going to tend to bind to a metal. So on histidine, we have this lone pair of electrons right here. That's actually going to bind to the iron, right? And likewise on the other histidine, it's going to be that same lone pair. Well, what is the charge on this histidine here? All right, the charge is 0. All right, when we end up creating a bond between an organic molecule and a metal, we say that the lone pair of electrons belongs still to the histidine. So even though those electrons are kind of being shared between the nitrogen and the iron, we say they still belong to the nitrogen. All right, so basically the amino acid here in this case is the same charge it would have had if it wasn't binding to the metal. So it's a neutral histidine here. All right, so we basically have two charges here that are neutral. All right, now what about for heme C? All right, well, with heme C, we have a methionine on it. All right, now for reasons I won't go into in really gory detail here, right? When we're sharing the electrons from the methionine, the sulfur here, it shares its electrons more with the iron than the nitrogen does. Right? So this sulfur actually is more of a positively charged sulfur, right? Whereas the histidine is really neutral. And there's other factors here like the protonation state of the histidine, things like that. We're not going to get into that. All right? But basically, this sulfur is we'll consider this to be a positively charged sulfur here. Now, thinking about the iron, right? If we have a positive charge next to the iron, is it going to want to be iron 2 or iron 3? Well, the answer is it's going to prefer to be iron 2. So for cytochrome C, it's going to prefer to be iron 2. All right, heme B, heme B is more so going to prefer iron 3. All right, it still prefers iron 2 to a certain extent, but it's going to more so prefer iron 3. All right, so now thinking about this, all right, what is a redox potential? All right, so redox potential, one definition is just, or the symbol for it is E0. Well, what are we talking about with a redox potential? We're talking about how easily a molecule gets reduced. So if we're talking about our heme B or our heme C, either one, in its oxidized form, so we'll have the iron 3 form for both of these, because we're going to want to reduce these. So the reduction potential is written for the reduction reaction. All right. So which one of these is going to prefer to become the 2+ form? Well, what we just said, what we just set up here is that cytochrome C prefers to be the iron 2 form. All right, so it's going to undergo this reaction to the right here more easily than heme B will. Heme B prefers iron 3 to a certain extent, so it's going to go to the left here more so. All right, now with E0 values, the more positive they are, the more favorable they are to go to the right. All right, so in this case, our bottom reaction is going to the right more so. So it is going to have a more positive E0 value. all right, because the sulfur on the methionine here, it has a positive charge to it.